Okay.
Okay, welcome everybody to the final colloquium of our semester series. So today we're very happy to have Avi Loeb. So he got his PhD in physics from the Hebrew University of Jerusalem in 1986, and he's been a long-term member of the Institute for Advanced Studies at Princeton, and then moved to faculty at Harvard Astronomy, where he's now the Frank Baird Professor of Science. He's held many influential positions. He was the longest serving chair of Harvard's Department of Astronomy. He's the founding director of Harvard's Black Hole Initiative. He's the director of the Institute for Theory and Computation in the Harvard Smithsonian Center for Astrophysics. He's a fellow of the American Academy of Arts and Sciences, the American Physical Society, International Academy of Astronautics, and he's a former member of the President's Council of Advisors on Science and Technology at the White House. He's written 8 books and hundreds of papers on a wide variety of topics, including black holes, the first stars, the search for extraterrestrial life, which we'll hear about today. He's won numerous prizes and awards. One interesting one is that in 2012, he was named by Time magazine as one of the 25 most influential people in space. So we're very fortunate to have him here today to tell us about extraterrestrial life, I presume. So please take it away.
Thank you so much, Kurt. It's really a great pleasure, and I wish we could meet in person rather than online. But first thing I should say is that you should not take too seriously all these labels that I acquired over the years. You know, I remember people like in the military being very proud of the medals they acquired over the years. But to me, all these labels do not mean much. And as Glenn Stockman can testify, I'm very much the same in spirit as I was at a much younger age. And also, you know, I grew up, as you will hear, on a farm, so you can pretty much regard me as a farm boy. Now let me share my screen. I hope it will work. Just one second, and then we can go through the slides. Okay, hopefully you're seeing my screen now. If not, let me know.
Looks good, but maybe you can make it big.
Yeah. It just takes a few seconds. Okay, so I will focus today on a book that just came out about a few months ago, couple of months ago, and it's in the middle of this first slide. It's called Extraterrestrial, and I should mention that within a couple of months there will be a textbook that will be coming out from Harvard University Press, shown on the right here, entitled "Life in the Cosmos." This textbook is more than 1,000 pages long, and the motivation is to lay out the foundation for what I regard as one of the most exciting frontiers in modern science, which is the search for life, either microbial life, primitive life, or intelligent life elsewhere beyond Earth. One of the reasons I'm very curious about intelligent life in space is because I don't often find it here on Earth. But anyway, if I had to summarize the content of the book that already came out, Extraterrestrial, I would summarize it with a sentence: when you are not ready to find exceptional things, you will never discover them. And that was the title of an essay that I published in Scientific American about half a year ago. What you see on the left here is a photograph of a picture that was hung on the walls of the Berlin Brandenburg Academy of Science and Humanities back in October 2020, about half a year ago. It was taken by the photographer Herlinde Quilbel, who came to my office and asked me to write on the palm of my hand what I regard to be the most important question in science. And I wrote, "Are we alone?" And if you think about life in the universe, actually the entire universe had roughly room temperature at a redshift of about 110, about 15 million years after the Big Bang. But that doesn't mean that life existed that early, because the bottleneck was not really the temperature. I mean, obviously you didn't need to be close to a star. You could be anywhere in the universe and you would feel comfortable at that point. The problem was that heavy elements were not produced in the Big Bang. So life as we know it requires water that has oxygen in it, and also carbon for carbon-based chemistry. And both carbon and oxygen are produced in the interiors of stars. And then you should ask, when were the first stars formed to make these elements? And that had to wait another 50 million years based on our standard cosmological model. And so the first forms of life could not have appeared earlier than about 70 million years after the Big Bang. We don't really know when it started. One way to search for an answer is to look at the stars in the halo of the Milky Way that are poor in heavy elements, that they represent perhaps the first generation of stars. And it turns out that often these stars are carbon enriched, and they have much more carbon per heavy element than typical. And that means that if they had any planets around them, they might be carbon-based planets. And if such planets transit the face of those stars, when we look at them in the sky, we can look for the composition of the atmospheres of those planets. And perhaps if we find evidence for biosignatures, molecules like oxygen or methane in the atmospheres, we might learn how early in the universe life started. But it's clear that if we wait very long, eventually life will stop, because all the stars will burn up their nuclear fuel, and that would happen around 10 trillion years from now. The universe would be quite empty if it will continue accelerating. In fact, our own galaxy will be embedded in the vacuum. You can see it on the left here. All the sources of light that we see beyond our own galaxy, which will be actually the merger product of the Milky Way and Andromeda, the two sister galaxies in the local group, all the galaxies beyond that will be carried away by the cosmic accelerated expansion. But the last stars would survive for 10 trillion years. These are the most common stars, dwarf stars. And after that, we will have to build our own nuclear reactors to keep ourselves warm. After decades of practicing astronomy, the biggest lesson that I've learned is that of modesty. And just to explain where I got it from, I want to refer to both my parents who passed away over the past few years, and read the 2 paragraphs from my book. My father David was laid to rest in the same red soil in which he planted trees all his life, in the vicinity of those plantations that he watered routinely, near the house that he built with his rugged hands and that I grew up in, surrounded by the people he loved and who loved him in return, under the blue sky that I study as an astronomer. My mother, Sarah, who put me on the road to thinking as a philosopher, with whom I spoke daily throughout my adulthood, and who especially gifted me with a life of the mind, was buried beside him 2 years later. In astronomy, we realize that matter takes new forms over time. The matter we are made of was produced in the hearts of massive stars that exploded. It assembled to make the earth that nourishes plants that feed our bodies. What are we then, if not just fleeting shapes taken by a few specks of material for a brief moment in cosmic history on the surface of one planet out of so many? We are insignificant, not just because the cosmos is so vast, but also because we ourselves are so tiny. Each of us is merely a transient structure that comes and goes, recorded in the minds of other transient structures. And that is all. And that brings me, when I see a picture, a painting like this one, showing a very proud emperor or a king that conquered a small piece of land on earth and felt very proud of himself, standing upright. Because what I learned from the universe is a sense of cosmic modesty. We now know that about half of all the sun-like stars host an Earth-sized planet roughly at the same separation as the Earth from the sun. And there are more habitable Earths in the observable volume of the universe than there are grains of sand on all beaches on Earth. So this emperor or king resembles an ant hugging a single grain of sand on the landscape of a huge beach. It's not very impressive. But I can understand where it's coming from when I looked at my daughters, and you can see them in this picture. When they were very young, they tended to think that they are at the center of the world, that they are the center of the universe, and they are the smartest. But then when we took them to the kindergarten, they met other kids, and that changed their perspective. Of course, if I were to ask them whether they prefer to stay at home, they would say yes, because this way they can maintain their illusion that they are the smartest and that they are at the center of the world. And if you look at human history, that's precisely what the ancient Greek philosopher Aristotle argued, that we are at the center of the universe, that there are spheres around us. And for 1,000 years, people believed him because it flattered their egos. But it turns out to be wrong. So that's an important lesson, that sometimes beautiful ideas are just incorrect, and evidence teaches us otherwise. And we should all aspire to get as much experimental confirmation for our ideas as possible. And sometimes it's not possible, so maybe we should move to other problems. That's just a comment to people that work on string theory. And my point is that our civilization will mature only by leaving home and meeting others, just like my daughters did. And we are probably not the sharpest cookies in the jar, where by the jar, I mean the Milky Way galaxy. And the reason I say that is if we look at the newspaper every day, we see news about humans doing things that do not make much sense. We invest a lot of resources on fighting each other, on feeling superior relative to others. It makes no sense if you look at the universe at large, because our differences are so minuscule relative to the big picture, and we live for such a short time. So why don't we focus on cooperating, working together towards a better future? That's a sign of intelligence. Now, Earth is our home right now, but not forever. There are all kinds of internal threats, like we're changing the climate. There could be wars that wipe out substantial fraction of the world's population. There are pandemics, there are political or technological catastrophes, self-inflicted wounds, so to speak. But there are also external threats. An asteroid may hit us. 66 million years ago, the dinosaurs were enjoying themselves eating grass. They had huge bodies, so they were dominant relative to their environment. And they were very arrogant at that point. They thought that nothing can affect them. But then a giant asteroid, a giant rock, the size of Manhattan Island, fell from the sky and killed them, wiped out 3/4 of all life forms on Earth. That's an important lesson. Even though you might think that worrying about the big picture is unimportant, that you can basically close your window curtains and just focus on problems at home, that's not a good approach. We learned that also during the pandemic. You can say, I don't want to read about what happens in the world, that doesn't affect me at all. But then guess what? Even if you get your food delivered through the front door, what happens in Wuhan, China affects what happens in your front door. So we need to go to space. It's clear that we don't want to keep all our eggs in one basket on Earth the way we do right now. And before I describe one approach for doing that, let me describe my personal history, because that's part of my book as well. I was born 59 years ago. You can see a picture of me at age 7 on the top left. I grew up on a farm, as I mentioned, and you can see the second image showing me collecting eggs. That was the routine every afternoon. And I used to drive the tractor, as shown in the middle image. I used to drive it every weekend to the hills of the village and read philosophy books. Philosophy was really my passion because it addresses the most fundamental questions we have. But then circumstances led me to astrophysics. I was I had to serve in the military, and I led a project that was funded by the Star Wars initiative of President Reagan, and that brought me to visit the US. And in one of the visits, I went to Princeton, and then I was offered the fellowship in astrophysics under the condition that I'll switch to astrophysics. And I ended up at Harvard. And then I realized that even though it was an arranged marriage, I'm actually married to my true love, because in astrophysics, we address fundamental questions using the scientific method. So philosophical questions can be addressed with science. And then I married my wife, and we have two daughters, as you can see on the right here. In May 2015, as you can see on the bottom left, a black limousine parked in front of the Center for Astrophysics at Harvard, and out of it came an entrepreneur from Silicon Valley named Yuri Milner. He came to my office, sat on the sofa in front of me, and asked whether I'm interested in leading a project to visit the nearest star system, Alpha Centauri, within his lifetime. And I immediately did the calculation. The nearest star is about 4 light years away. The signal about the 2016 elections just arrived there in February this year. And to get there in 2 decades requires a spacecraft that moves at a fifth of the speed of light. That's 1,000 times faster than any chemical rocket that we have launched in the past. It's sort of a factor of 1,000 is roughly the difference of the ratio in speed between Sputnik and Ford's T-car, the difference between a spacecraft and a car. So I told Yuri I need 6 months to think about it, and then with my students and postdocs, we came up with only one technology that can achieve that. That seems reasonable, and that is a light sail approach, and I'll describe it in a minute. And we announced it as you can see in the middle bottom image, we announced it in April 2016 in the company of Stephen Hawking that came for that announcement, and also Freeman Dyson is shown in the middle there. So let me describe sort of the big picture here. The sun is on the left, and then at 10 times the Earth-Sun separation, you see Saturn. And at 100 times the Earth-Sun separation, that's where the solar wind, the wind coming off the sun, that's where it's being stopped by the gas that fills in the void between stars, the so-called interstellar medium. But the solar system does not stop there. I mean, the big planets stop roughly there. That's where the Kuiper belt is also. But the solar system continues to a distance that is 1,000 times larger. Most of the volume is actually called the Oort cloud. And that's a collection of bricks that were left over from the construction project of the solar system, of the planets in the solar system. These are rocks, so-called planetesimals left over. And they were scattered into the spherical volume of the Oort cloud that goes roughly halfway to the nearest star. So if the nearest star has an Oort cloud of itself, then all these Oort clouds touch each other, just like densely packed billiard balls. And so when stars move relative to each other, some of these rocks can be dislodged into interstellar space because they're very loosely bound to their parent stars. And the nearest star is Proxima Centauri. It has a planet, it so happens, in the habitable zone. This star is actually 12% of the mass of the sun, so it's a dwarf star. Most of the stars in the Milky Way are much smaller than the sun. The sun is not typical. And they are dwarf stars, just like Proxima Centauri, they emit mostly in the infrared. And because the star is very faint, the habitable zone is much closer to it. It's about 20 times closer than the Earth is from the sun. And it so happens that there is a planet there. It's called Proxima b. And because this planet is so close to the star, it faces the star with the same side. It's tidally locked. Just like the moon is tidally locked to the Earth, we see always the same side of the moon. So there is a permanent day side to this planet, Proxima b, and a permanent night side. And my daughters say that if we ever move there, they want a house on the strip that separates these two sides, because that's where you can see the sunset forever. Just think about it. You're sitting at your porch and you see the sunset forever. If there are any creatures on the day side, they have eyes that are sensitive to the infrared. And I actually asked my students in the freshman seminar class that I'm teaching at Harvard, I asked them if they know of any animal that has infrared eyes. And one of them showed an image of a shrimp that lives deep underwater and has infrared eyes. And they look like ping pong balls connected with cords to the head of the shrimp. It does really look like an alien, this shrimp. But you can sort of understand why we don't have visits of such creatures, because all we can offer in our vacation sites are green lawns illuminated by visible light. And visible light hurts their eyes, and they are used to dark red grass. So interstellar tourist agencies will never advertise the Earth as a desired destination for them. We have to go there and entice them. So speaking about going there, what is the technology that could allow us to visit the nearest star within, let's say, decades from now? And that's the Starshot initiative that I mentioned. The idea is to have a sail, a thin film of material that is being pushed by light, by a very powerful laser beam that is about 100 gigawatt. And if the sail weighs less than a gram, or of order a gram, then within a few minutes, you can launch it to a fifth of the speed of light across a distance that is 5 times the distance to the moon. And if you attach miniaturized electronics on the sail, that can include a camera, navigation device, communication device, then you get a spacecraft. And a light sail technology was demonstrated already with using the sunlight as the drive. You can see it on the right side. That's a Light Sail 2 that was deployed by the Planetary Society less than a couple of years ago. So here is the concept. A lot of low power lasers are combined to make a very powerful beam that shines on a sail that is roughly the size of a person, a few meters in size. And a diffraction limited laser beam can be focused on such a scale across a distance that is 5 times the distance to the moon. And it will push it, if the sail weighs of order a gram, it will push it to a fifth of the speed of light. And in principle, such a sail can be released once a day from a mother spacecraft. And then after the first few minutes, it will coast for 20 years. That gives a different meaning to Steven Weinberg's first few minutes. I just thought about it. At any event, it's a very long journey, and once it gets to the Proxima Centauri system, it could pass close to the planet and take a photograph, and eventually beam the signal towards Earth. And of course, because the distance is so huge, 4 light years, the beam, oops, sorry about that. The beam will take a long time to reach us, and will spread during that time, and we need a very powerful telescope to detect the signal. This is called the Starshot initiative, and we are currently working on it with many teams that are demonstrating the technology necessary for making this happen. Oops. So the fundamental question is not only whether there is life on the nearest star, but is there intelligent life anywhere nearby? Are we the smartest kid on the block? And as I said, I'm pessimistic that we are the smartest kid on the block, because if you look at recipe books of cakes, you see that out of the same ingredients, you can make very different cakes depending on how you mix the ingredients and how much heat you apply in the process. And what's the chance that by taking the chemicals that existed on early Earth, you would get the most tasty cake? Quite small. But without a prejudice. I mean, some people argue that we are special and unique, and you know, just like my daughters, that they are the smartest. But without a prejudice, let's just be open-minded and search. I think that's the best way to get educated. Let's check who is in our neighborhood, what kind of neighbors we have. And the first place to check is in our backyard. So it turns out that on October 19th, 2017, the first object from outside the solar system was discovered near Earth. It was discovered by the Pan-STARRS telescope on the summit of Haleakala in Maui, Hawaii, and given the name Oumuamua, which means a scout in the Hawaiian language. You can see this object circled in blue in the middle of this image. And since it moves very fast on the sky, if you were to focus on it, you would see the stars appearing as a sequence of dots when you take snapshots, because they move relative to the object. That's what you see here as the series of dots. And this is an illustration of the trajectory of the object on the sky. It started from the top right, and there is...
What?
You want to call?
I'm listening to a seminar.
Whoever is speaking
with
should
Fred.
mute himself. If there is anyone in the audience who is an amateur astronomer, oops, am I muted or can you hear me? You can hear me?
You're fine.
You're okay.
You're good.
Okay. If you look at the upper right corner, you see the words solar apex, which refer to the direction of motion of the sun in the so-called local standard of rest. And the local standard of rest is simply the frame of reference that you get to when you average over the random motions of all the stars in the vicinity of the sun. So it's sort of like the local galactic parking lot. And all the stars move relative to the local standard of rest, roughly at tens of kilometers per second. And it turns out that Oumuamua was at rest in that frame. Only 1 in 500 stars is so much at rest as Oumuamua was. So that's already making it quite unusual, because if it came, let's say, from an Oort cloud of another star, it should have inherited the motion of the parent star, but it didn't really move relative to the local standard of rest. So the way to think of it is it was just like a buoy sitting at rest on the surface of the ocean, and the sun bumped into it like a giant ship and gave it a kick through the gravitational force. It scattered it. And here you can see the kick. So the relative motion between us and the Oumuamua was simply the motion of the sun relative to the local standard of rest. And the other peculiar fact about this object was that as it was tumbling on the sky, as it was rotating every 8 hours, the amount of light, sunlight, reflected from it changed by a factor of 10. The way we discover objects is by using the sun as a lamppost that illuminates the darkness of space. So when an object passes close to the sun, we can see it because the sun illuminates it. But this object, as it was tumbling, changed its brightness by a factor of 10, which is very unusual. For all the solar system objects, the comets or asteroids we've seen before, the variation is usually less than a factor of 3. So that implied this object must have an extreme shape. And in fact, the best fit to the light curve was that of a flat object, pancake shape, at a 90% confidence level. So it was not cigar shaped, it was pancake shaped. And this is again the orbit of this object, Oumuamua, starting from the top right in July 2017 and ending on the left in October 2017. As it turns out, I was with my family, we were visiting that observatory in July 2017. I was asked to give a colloquium there, and we went to that observatory that includes also a solar telescope that was just about to be constructed at that point. It's a beautiful location above the clouds over there. But we didn't know about Oumuamua when I visited the Pan-STARRS observatory. So it turns out this object is rather weird. There was a question about it at Harvard, and when I left the room with a colleague of mine that worked on rocks for decades, he said, this object is so weird, I wish it never existed. It obviously takes people out of their comfort zone. But to me, it's exciting. When we see something unusual, when we have anomalies, it may imply that we can learn something new. So why should science be boring? Why not pay attention to anomalies rather than say, I wish they never existed? To anyone working in particle astrophysics, anomalies are really the lifeblood of that frontier. So what are the strange properties? Well, first of all, we didn't expect to find an object with Pan-STARRS because I wrote a paper a decade earlier that forecasted how many rocks we should see based on what we know about the solar system, how many interstellar rocks. And the answer was off by 2 to 8 orders of magnitude. So even the most optimistic assessment was that Pan-STARRS will not see anything by a factor of 100. There are too few of these objects. So the actual discovery of this object was a surprise. But beyond that, it came from the local standard of rest. Only 1 in 500 stars are so much at rest there. Its brightness changed by a factor of 10, a very extreme shape, most likely pancake-like at the 90% confidence. There was no heat or infrared light observed by the Spitzer Space Telescope. So that implied that it's smaller than about 200 meters because we know how hot it must have gotten based on its trajectory, and we didn't see the emission from it, so that implied that it must be small. And the fact that it's small means that it has a high reflectance of sunlight because we know how much sunlight we receive. So if it were 20 meters in size, it should have been a perfect mirror. So somewhere between 20 meters and 200 meters. And the most peculiar fact is there was no cometary tail. The Spitzer Space Telescope didn't detect any carbon-based molecules or dust around it. So it was definitely not a comet, but yet it exhibited an excess push away from the sun. And this extra force that was acting on it declined inversely with distance squared in a very smooth fashion. So to me, that suggested that perhaps it's being pushed by reflecting sunlight, just like a light sail. But nature doesn't make light sails. So that led me to suggest maybe it was manufactured by another civilization. At least it's a possibility we should put on the table. And then after this proposal was made, there were mainstream suggestions for explaining Oumuamua as a result of a natural process. And I should say upfront that all 4 suggestions that were made over the past 2 years associate Oumuamua with something we have never seen before. So my point is simple. If it's something we have never seen before, we should definitely keep the possibility that it's artificial in origin on the table. So what were the proposals? One of them suggested, well, maybe it's a cloud of dust particles that are very loosely bound, just like a dust bunny that you find at home, the size of a football field, but so lightweight, 100 times less dense than air, so that by reflecting sunlight, it gets pushed, just like a feather. The problem with that is a cloud of dust particles that is 100 times less dense than air would not have the material strength to withstand the heating by hundreds of degrees as it gets close to the sun. There was another suggestion that it's a fragment from the tidal disruption of a bigger object that passed very close to a star. Well, first of all, the chance of passing close to a star is very small. So why would the first object we see be the result of a bigger object passing close to a star? But then secondly, from tidal disruption, you get elongated objects that look like a cigar. You don't get pancake-shaped objects. Then there was the suggestion that maybe it's a hydrogen iceberg, a chunk of frozen hydrogen, roughly the size of a football field. We've never seen frozen hydrogen produced in molecular clouds, in the Milky Way galaxy. We've never seen evidence for that. But the idea was that maybe then the cometary tail, exists, but hydrogen is transparent, so we can't see it. The problem with this idea, and we wrote a paper about it with a colleague of mine, Thim Huang, is that such an object would get evaporated very quickly. It could not survive the journey through interstellar space because of heating by starlight. So then very recently, there was a suggestion of a nitrogen iceberg that was chipped off a planet like Pluto. We know that on the surface of Pluto, there is solid nitrogen. It characterizes a very thin layer, only a few % of the size of Pluto. But the idea is, suppose you have a lot of Plutos out there around other stars, and they get bombarded by rocks, and these collision processes just chip off icebergs of pure nitrogen. Again, we've never seen anything like it in the solar system. You ask yourself, okay, well, if nitrogen icebergs are common, why haven't we seen it in the solar system? Why didn't the Pluto itself produce it? Why don't we see it here? Why does it have to be produced around other stars? And it turns out the biggest problem with this scenario is discussed in a paper we wrote a couple of weeks ago with my student, Amir Siraj, where we showed that the mass budget just doesn't work out. Even if you chip off more than 10% of all the surfaces of Plutos around other stars, you need 100 times more mass than you have available in stars in the Milky Way galaxy. There is just too little mass in stars to produce enough Plutos whose surfaces will be chipped off to produce an Oumuamua-like object with a high enough abundance so that pan-stars will discover it. It just doesn't work out. And the math is really simple. You just take the number density of stars in the Milky Way galaxy, and then you know the heavy element fraction of that mass that is locked in stars. You put it in planets, and there is just not enough heavy elements to account for a big enough population of objects that will account for Oumuamua. I can go into the details, but it's in our paper on the archive. You can find them. This is the one of the first reviews about my book that was published in Goodreads. And I didn't understand a couple of words in this sentence. I asked my daughters and they explained it to me. But the way I understand the situation is similar to the experience you have when you walk on the beach. Most of the time you see rocks or seashells that were naturally produced. But every now and then you see a plastic bottle that tells you an important story, because even if it's punctured and dysfunctional, it says that there is a civilization out there. And if you judge by what we sent into space, Voyager 1, Voyager 2, New Horizons, within a few billion years, these objects will not be functional anymore. And most of the stars were born billions of years before the sun. So there could be a lot of equipment out there, and it keeps accumulating. Turns out that there was another object that showed an excess push away from the sun as a result of reflecting sunlight without a cometary tail. It was discovered in September 2020, just about half a year ago. And it was given the astronomical name 2020 SO. You can find a Wikipedia page on it. And then it was discovered by the same telescope, Pan-STARRS, and the astronomers that discovered it realized, after extrapolating the orbit, the trajectory back in time, they realized that it came from Earth. What you see in this video is the motion of this object around Earth. And it actually turned out to be a rocket booster that was launched into space in 1966 as part of a lunar lander mission. And the reason it exhibited an excess push from the sun by reflecting sunlight is because it had very thin walls. So it had a large area for its mass. And we know that it's artificial because we produced this object. We just don't know who produced Oumuamua. There was a second interstellar object discovered in 2019 by an amateur astronomer from Russia called Gennady Borisov. It was given the name Borisov. And this happened to be a comet. It looked just like the comets we usually see in the solar system. And so my colleagues came to me and said, well, it's clear that Borisov is natural. Doesn't it convince you that Oumuamua was also natural in origin? To which I said, when I find a plastic bottle on the beach and after that I find rocks, it doesn't make the plastic bottle a rock. When I met my wife, she impressed me as unusual on the first date. I met a lot of women after that and I didn't change my opinion. So the fundamental question is whether Oumuamua was natural or artificial in origin. And the best way to find out is to take a photograph of the next interstellar object that looks as weird as Oumuamua. And when I go to the kitchen and I see an ant, I get alarmed because I know that there must be many more ants out there. So if we continue to monitor the sky, even with Pan-STARRS, within a few years, we're supposed to find another one. But with the Vera Rubin Observatory that will come online in a couple of years, we could find one every month. And if we get an alert a year in advance, we can send a spacecraft equipped with a camera that will take a close-up photograph of that object. And, they say a picture is worth 1,000 words. In my case, a picture is worth 66,000 words, the number of words in my book. I wouldn't need to write my book if we had a photograph. We could have easily found out whether it's a natural object or an artificial one. So we can find the truth experimentally. We don't need to argue about it. That's why I don't understand why people get emotional about this subject. What you see here is an image taken by OSIRIS-REx, a mission sent in the direction of the asteroid Bennu. And you can easily tell from this image that it's a natural rock. I mean, it has a lot of small rocks on the surface. And the OSIRIS-REx goal was to take a sample, collect a sample from Bennu, and eventually deliver it back to Earth. Just imagine a similar image taken of an artificial object. We might be able to read off the label, made on planet X. We could even import the technology back to Earth. And that would save us a lot of years developing the same technology ourselves. So there is a lot for us to that we can learn from finding equipment in space. I should also comment that the moon is like a museum, because the moon doesn't have an atmosphere that burns up everything that falls on it. The Earth has an atmosphere. We see these objects, small objects burning up. They're called meteors. If they are bigger than the size of a person, the cores of those objects can survive and eventually impact the Earth. But the moon doesn't have an atmosphere, so everything that impacts it is collected on its surface. It also doesn't have geological activity. So if we ever establish a sustainable base on the moon, we should regard it as an archaeological site and search for any interstellar equipment that may have impacted it. There are also trapped interstellar objects in the solar system. Those are objects that pass close to Jupiter. And Jupiter and the sun can act as a gravitational fishing net. An object passing close enough to Jupiter can give Jupiter a kick, lose some of its energy, and get trapped in the solar system. And we calculated that there should be thousands of those objects actually trapped right now. So in principle, we can aim to visit those objects. They would not be in the same plane as the planets are orbiting the sun. They should come from some random direction. So one can easily trace candidate objects. And there are some. After we wrote this paper, some were identified. Now, if you think about the universe at large, this is a depiction of the history of the universe, starting with a Big Bang on the left. That was 13.8 billion years ago. We developed our technologies only over the past 100 years. That's 1 part in 100 million of the age of the universe. So if you just think about it, most stars formed billions of years before the sun, and there could have been a lot of civilizations around those stars that are dead by now. But we can find evidence for them, even if they're not alive. In the past 70 years, we searched for radio signals. But that's the wrong approach, because it's just like trying to have a phone conversation. You need the counterpart to be alive. We cannot have a phone conversation with the Mayan culture. The Mayans are gone. But we can find evidence that they existed in archaeological sites. So I argue for space archaeology. And of course, to find evidence for other civilizations, you need to look at the right place around stars. And that depends on the type of star. The habitable zone is in different locations, different distances from the star, depending on its surface temperature and mass. Aside from relics that I was discussing before, equipment in space, one can look for industrial pollution. We wrote about it in 2015 with a student of mine. One can search for artificial lights on the night side of a planet. One can search for photovoltaic cells on the surface of a planet. They reflect, there is a spectral edge for photovoltaic cells that you can look for. One can search for light beams that sweep across the sky and create a flash of light. And one can search for swarms of satellites surrounding a planet, a habitable planet. I should also mention that light sails could be launched to near the speed of light, even without a powerful laser beam. If you park light sails within 100 times the Earth-Sun separation around a massive star that is about to explode as a supernova, then the flash of light from the explosion of the star could push the light sails close to the speed of light. The situation is similar to surfers waiting for a giant wave on the beach of Hawaii, except in this case, the wave is a wave of light. And it's similar to dandelion seeds that you can see on the right side here, carried by the wind. So just imagine those light sails being pushed out of an exploding stars near the speed of light. Now, Enrico Fermi, about 70 years ago, asked an important question. He said, where is everybody? If they exist out there, why don't we see them? Well, that's a very presumptuous question, because it assumes that we are interesting enough for them to pay attention to us. Frankly, I don't think so. I think we are as common as ants are on a sidewalk. We are not that interesting. We just developed our technologies over the past century. When I met my wife, she had friends that used to wait for Prince Charming on a white horse that will come and make them a marriage proposal. That never happened. And then they had to compromise. So why should we believe that we are sufficiently interesting for someone to come over and have a party in our backyard? Most likely, in addition to this, most civilizations are dead by now. Look at how we behave. We might survive only a few centuries into the future. So there might be a very narrow window of opportunity to interact with such civilizations. But that doesn't mean that we cannot find evidence for them. As I argued before, we can engage in archaeology, in space archaeology, in searching for relics left behind by these civilizations. And my hope is that by finding such relics of civilizations that perished as a result of misbehaving, it will teach us an important historical lesson. It will give us inspiration to get our act together and avoid a similar fate. Thank you. I'll be glad to answer questions. Let me stop the sharing. And I guess Glenn muted everyone, but we should unmute whoever wants to ask a question.
Great. So if you have a question, you can raise your hand or type it in the chat. You want to start us off, Glenn?
Sure, Avi. Fascinating talk. So the breakthrough light sails are going to reach Alpha, Proxima at moving very fast. So they're not going to get much of a chance to visit. But yet Oumuamua managed to get here traveling really pretty slowly. So is it just that the people who inhabit Oumuamua have lifetimes that are much longer than us and so are much more patient, or have they figured out how to slow down?
Well, I would guess that it's a dysfunctional piece of equipment, that it could be a surface layer of a spacecraft, or it could be the fact that it came from the local standard of rest may say something, because there may be a grid of those objects out there that is used for finding your coordinates when you're traveling through interstellar space. It may be like road posts, and we just bumped into one of them. It may be a relay station for communication. I don't know what its purpose is, and I don't know whether it's functional. It probably is not functional after billions of years, but it's very different in spirit than the Starshot spacecraft. as you say, Starshot moves very fast. This is just because Yuri Milner has a short lifespan. You know, if we could make his life a million years, then we could use chemical rockets. So one solution to his suggestion was to extend his lifespan to 1 million years and then use just chemical rockets. You know, that would also be appropriate, but at the moment we don't know how to do that. Just think about the tenure system. If all of us lived for 1 million years, it wouldn't be really a good system. But anyway, so an interesting point is that if there are, you know, Starshot-like objects passing through the solar system, we would never recognize them because, first of all, they would move extremely fast across the sky. So astronomers would completely ignore them. They would think, you know, these fast streaks on their CCD frames are probably cosmic rays or something else, you know. They would just ignore that because they are looking for objects moving at tens of kilometers per second, basically, most of the time. And then also, you know, the kind of object we are designing is the size of a few meters. That's much too small. It doesn't reflect much sunlight for any survey telescope that we have or plan to detect it. So there might be many more objects passing the solar system, moving at high speeds or of much smaller size that come from interstellar space. And I think, you know, all I'm trying to suggest is that we monitor them because every now and then we might find a plastic bottle among the rocks that we see. And it's just a wake-up call, a completely new way of searching, you know, that was not practiced in the past. But the response that I get is people saying, business as usual, forget about it. There are anomalies, but I don't really care about the details. And, you know, that's not really a smart approach. It reminds me of the way that philosophers responded to Galileo's proposal that the Earth moves around the sun. They said, we don't want to look through a telescope. And by the way, you know, we will put you in house arrest because we don't want you to speak freely about this. And all that did was maintain their ignorance longer. It didn't change the fact that the Earth moves around the sun. So my point is, reality is whatever it is, you know, irrespective of whether we ignore it. And knowledge is always good for us. So, and by the way, all of these proposals for Oumuamua that made it a natural object, they all talk about something we've never seen before, like a nitrogen iceberg or a hydrogen iceberg. We have to come up with an explanation for the nurseries that make such objects, and it will teach us something new no matter what. So we should be intrigued by the evidence and try to collect as much data as possible on future objects. The only way we will not learn something new is if we ignore it.
Harsh, I think you're next.
Sure. Well, actually, I think my question was partly addressed. I was going to ask what the significance would be of, you know, if we had the technology, why would we want to place an object in local rest? What would be the purpose of that? But let me ask a sort of related question, which is, it made a very close pass into the inner solar system. So that seems like that's got to be intentional, right? Rather than it was just passing through. It's not like a Voyager-like object which somehow just swung by.
Well, we wouldn't see objects that have a larger impact parameter relative to the sun. You see that. So there are two ways to interpret this object. One is to say, oh, it's just, you know, a random occurrence. You know, there is a population of such objects with an isotropic velocity distribution, and we've just seen one of them that passed close enough. In that case, you need a quadrillion of these objects right now in the solar system. You need 10 to the power 15 objects, roughly one per volume associated with the orbit of the Earth around the sun. That's a huge number. That's why the mass budget is so daunting. You know, if you make it a rock, you need a lot of rocks, 10 to the power 15 of, you know, rocks the size of a football field, and that's a lot. If you make it a light sail, you need much less mass because it's very thin. But still, it's quite unusual, a quadrillion. I mean, you can think about von Neumann machines that replicate themselves and make a lot of them. But another option is that it wasn't targeted, the trajectory was not random, that in fact it was radial into the habitable zone of the solar system, and then you need a much smaller number of such objects, as you indicated. Yeah.
Doesn't that argue against the galactic flotsam suggestion that suggests that if it's artificial, it was probably directed?
Yeah, well, that's one. But you have to keep in mind that it took 10,000 years for this object to traverse the Oort cloud. And we were not that interesting 10,000 years ago. So even if it was aiming to visit the inner part, it's not because of us. It's just because of the habitable zone being there. Because 10,000 years ago, we were just like animals. Well, not really. We were dressed up, I guess, but we didn't have any technology.
Well, you're going to Proxima without any knowledge about what's over there, so.
Right.
Oh yes, thank you. Thank you for your really refreshing talk. I really appreciate that. So the question that I have is regarding, biosignatures. I saw that you have this, you didn't mention your talk, but you have this in your front cover, in the front cover of your book. So can you please tell me what you exactly mean there? And if this has something to do with chirality? Because as you know, in the Viking mission in 1976, chirality in the sense of the biomolecules, biosignatures, has a very important role. So I wanted to ask if that is what you mean, or if something else.
Well, that's an interest. So you're asking about chirality as a signature of life? Is that
right? Yes. Yeah,
that's a very interesting point, because we don't fully understand where the preferred chirality of all the DNA we find on Earth. Why was it chosen? And there is a possibility that it's just the symmetry breaking that was random, and then one form of life dominated, and the other option just was completely suppressed. And that's what most people would think, but we don't really know what the reason is. And there are some papers in the literature, not many, but there are papers suggesting physical mechanisms for choosing one, breaking the symmetry. Now the interesting point is, Perseverance, there is this mission to Mars. It's looking for early life on Mars, when Mars had an atmosphere, and it will search the surface. And it's very likely, that Mars had oceans. And in fact, Mars and Earth exchange rocks. So it's possible that life was shared between the planets. And in fact, it's possible that we are all Martians, that life started on Mars and came to Earth. But one way to find out is to check if we find the evidence for molecules indicative of life, or structures indicative of life, if we find any traces from the past of Mars, whether chirality was the same as on Earth, if we can ever identify it there. And if it is, well, if the DNA looks similar to that on Earth, then it may imply that it was shared between the planets. But if we find the life to be completely different there than on Earth, it would mean two things. First, that it was not shared. And second, that there are multiple paths to making life. And, we are still at the infancy of this field. I should also just make a footnote that one way to expand our imagination is to produce life in the laboratory. And a colleague of mine at Harvard named Jack Szostak, who got the Nobel Prize already once, he's on his way to get a second Nobel Prize, because he's trying to produce synthetic life in the laboratory and has been working on that for a decade. And if we're able to generate synthetic life in the laboratory, then we can play with initial conditions and with the circumstances and see whether we can understand, for example, why chirality is being chosen and why life goes one way. Why is it in liquid water, or maybe it could be in other liquids? it will definitely expand our imagination. Just like in physics, you know, once we started doing experiments, we understood fundamental physics so much better.
Thanks.
Stacy, did you want to ask your question? I think
Yes, you're muted, whoever.
Yeah, so I guess Stacy McGaw had a question in the chat, which is how sound is the evidence for the acceleration of this object?
Oh,
that
that's
seems
an excellent
critical.
question, because yeah, that's an excellent question. And I had a postdoc. You know, the worry is maybe the acceleration was an error, you know, like, even though it was published in Nature and, you know, was refereed carefully. And so I had a postdoc that looked for months at the data and tried to analyze the same data completely independently, out of scratch, and basically retrieve the same answer with the same significance. And so at least from my experience, it looks like the analysis was correct. And now it's always possible that the data points that were reported had an error, but the strange thing is that it does, I mean, the signal does decline inversely with distance squared in a smooth fashion. So it's not like a random fluctuation at one point along the orbit. And I should say that if it was evaporation of gas, very often, comets have a jitter because there are jets, there are special locations on the surface of the comet that emit the gas. And because of that, there is some jitter variation. And also at a certain distance from the sun, water does not get evaporate, does not sublimate anymore. So the force acting on a comet stops. And in fact, Oumuamua reached that point and there was no sudden change in the force. So it was not consistent with ice evaporation, this extra force.
Walter, you're next.
Yeah, very nice talk. My question is about how you define the habitable zone. I mean, what kind of assumptions does that make about how similar, you know, any kind of form of life in the universe would be related to the one we know?
Right. So the habitable zone is not really saying that life must occur there. It basically says, in terms of the physical conditions, the surface temperature of an object in that region would allow liquid water on the surface, you know. So so the Earth, by the way, the Earth, just so that you know, the Earth is sort of at the edge. It could be at the edge of the habitable zone. That's why the Earth went through snowball phases. It froze in the past. So the Earth should have been cooler than it is. It's warmed up by the greenhouse, you know, by the fact that we have some atmosphere that keeps it warm. We have this blanket. And now we are making it potentially even warmer. But there is a habitable zone around the sun that can be defined in different ways, but the simplest ways is just regarding the surface temperature that allows liquid water to exist. And of course, you have to take into account the albedo, the reflectivity of the surface, and how much light is absorbed, and whether it has an atmosphere or not that keeps it warm, because energy is being radiated back into space, and so there are some losses from the surface. So that has to be modeled, but that is the simplest approach. And that assumes life as we know it, as you said, that requires liquid water. So to have liquid water, you need the surface temperature to be right, but you also need an atmosphere, because if you take solid ice, water ice, and put it in vacuum and warm it up, it goes straight into gas, it sublimates. And so the only way to make it liquid is by having an external pressure. And that's why you need an atmosphere. It turns out that to keep an atmosphere, you need a planet roughly the mass of the Earth, a planet that is 10 times smaller than the Earth, like 10 times lesser in mass, like Mars lost its atmosphere. We have an example. That's a warning sign. So anything smaller than Mars cannot keep its atmosphere in the habitable zone. And it's also possible that near very small stars, dwarf stars like Proxima Centauri, simply because you are closer to the star, the atmosphere is stripped by the stellar wind, and life is not possible. That may explain why we live next to the sun. You know, we were much more likely to live next to a dwarf star because these are the most common stars. But perhaps we live next to the sun because we can be far enough from the sun so that the wind does not strip our atmosphere.
In other words, it's a conservative assumption about that life would be similar to.
Yes, it's
Well,
we have a whole chapter in our book that will be published in 2 months dedicated to exactly your question. And if you're interested in the details, just have a look. It will come out at the end of June this year by Harvard University Press, called Life in the Cosmos.
Kathy, you're next.
So when I first heard about solar sails, I was so excited by a possibility that is almost as exciting as what you have described today, which is that undergraduate students could conceive of and develop an experiment to go to Mars, launch it, have the experiment arrive on the surface of Mars in 5 minutes, and get feedback, and the idea of fast feedback on what's happening in our own solar system in terms of whether there is life or life producing conditions within our solar system is just so exciting, and that it can be done possibly so inexpensively and with such rapid feedback. I wondered if you have comments on that.
Yes, that's an excellent point. You are exactly right that maybe the best utility of this technology would be to visit places in the solar system very quickly. It would take a few days to reach Pluto, for example. It took 9.5 years for New Horizons to get there. We can go through the plumes of Enceladus and check if these are geysers coming out of the icy surface of Enceladus, and people think there is an ocean underneath. And if there is fish in that ocean, maybe there are molecules in those geysers that we can find that are indicative of biological life down there. And you are exactly right. And in fact, when we announced the Starshot initiative, I made that comment along the lines that you pointed out, and I very much hope that this would be the future. I should also say that you can, using the same technology, you can imagine much slower spacecraft that don't move at a fraction of the speed of light, but move faster than chemical rockets, but they carry a much bigger payload. And in 2016, we wrote a paper with my postdoc, James Gwillichon, where we said, if we look at other planetary systems and we look for conjunction when you have two planets along our line of sight, just like imagine Earth and Mars lining up in the direction of the line of sight of another observer, then we might be able to see the beam of light that is used to propel a light sail that travels between the two planets. So that would be an interesting thing to search for. When you see a flash of light coming from a planetary system, when two of the planets like Earth and Mars line up along the line of sight, then oh, they might have light sails allowing them to travel from one planet to the other.
Thank you.
Right, I think we should end our formal part of this. So thank you everyone for coming, and let's thank Avi again.
Thank you for hosting me.
So we'll end the
Pleasure.
recording, and if there's